Hey, it's Linford here, and we're going to be talking today about rational exponents. In particular, we're going to be talking about how to convert radicals to exponents, and then we're going to be talking about a couple different properties of rational exponents. Starting off, we've got to define what is a rational exponent. Okay, if I took any root, so I have some radicand, and I'm taking a root of that, so the nth root. The nth root is actually a rational exponent. This means that the exponent is like a fraction, 1 over n. If I took the nth root of something, I'm really taking it to the 1 over n power. So really here, we're seeing that radicals are really just a type of exponent. That's kind of what's going on here. It's a type of exponent, except instead of having this exponential growth, we're breaking it down much more. So if I was to define the square root for you, if I was to take the square root of a, this is going to be a to the 1/2 power. Oftentimes, this is how you would have to type it into your calculator. Some of the new TI models have ways for you to input different roots very easily, but some of the scientific calculators don't always have that computing power. So if you had to take the fourth root of, oh gosh, I don't know, 50, let's say, you would put in your calculator 50 to the 1/4 power. And that's how you're going to tell your calculator to actually compute a 1/4 root or a fourth root. You just put it as an exponent. So if I was to start converting between radical exponents and rational exponents and radicals, I would know that this denominator is my root. Anytime you have a denominator as an in an exponent, that's what root you're taking. And it might be easier to see if we split it up kind of like this. Here's one way of doing it. I have x to the 4th times x to the 1/5. So I'm really taking x, raising it to the 4th power, but then this 1/5 here says, hey, take this to the 5th root. That's all that that's saying. So when you have rational exponents, the numerator is your exponent. That's the one that behaves just like a normal exponent does, the numerator. The denominator, this denominator is your root. That's the thing that controls what root you're taking. So if I was practicing this a little more, I would say, okay, I'm taking 15 and I'm multiplying it by a to the 1/2 power. Now remember, exponents only affect what they're immediately touching. So this 1/2 is only affecting the a. So I have 15 times the square root of a. We are taking the square root of a. My root is 2. Remember, there's an imaginary index of 2 there for the square root. And then if I was to try to convert a radical to an exponent, I would say, well, I'm taking y, and I'm raising it to the 3rd power. That, of course, stays. Oops. The 3rd power. That's what's going to stay. However, I have this as my root, so I'm going to make y to the 3/4 power. 3 because I'm cubing it, like I did under the radical, but then 3/4, the denominator 4, because I'm taking the 4th root of it. Hopefully this is starting to make a bit more sense, but let's try practicing some properties that we have when we start working with rational exponents. So these should start looking pretty familiar. So these are all properties of integer exponents, so let's see what happens if I have fractions as my exponent. So the multiplication of like bases. If I have the same base and I'm multiplying it together, I'm going to say that we just add the exponents, just like we did before. oops, there we go. If we're multiplying the same base, all we have to do are add the exponents. Well, okay, to add these, however, we have to do an extra step. We got to find a common denominator, don't we? So let's just make that x to the 4/12 power plus 9/12. There we go. And this is it. This is all that we're doing. If you have the multiplication of like bases, you can go ahead and add the exponents together. So that becomes x to the 13/12 power. And if you wanted to, you could convert that to radicals. That would be x to the 13th to the 12th power. Now, when it comes to the division of like bases, we're going to do the same thing that we did before. We're going to go and subtract the exponents. If you are dividing things that are the same base, all you have to do is subtract their exponents. So we end up with y to the 2/5 power. Take a sec, test yourself, see if you can convert this really quickly into radicals. All right. Let's see what you got. I would have taken y and squared it, because that's what my numerator says to do. And then I would have taken it to the 5th root, because that's what my denominator says to do. Hopefully that was starting to make sense to you. This is being able to convert between radicals and exponents, because really it's a powerful idea that we realize that they're the same thing. So all of these rules should be pretty much the same. Now here's one we all know and love, the power rule. The power rule says if you have some base to an exponent and you raise it to another exponent, all you have to do is multiply the two exponents together. So that's x to the 2/3 power. That's a terrible 3. To the 2/3 power. Or we could write that as the third root of x squared. Now, a power of a product rule, this is the one that we said, hey, this is going to behave kind of like distribution. Again, it's not distribution. This is not the distributive property, okay? But it kind of behaves a little bit like that. What we say is we're going to apply the exponent to the 4 and the x squared. So we take 4 to the 1/5 power and x squared to the 1/5 power. So that's 4 to the 1/5 times x to the 2/5. And this is what it would be if we wanted to write it in rational exponents. However, we could also write this as a radical. See what you think. It might be helpful if I could give you a little bit of a hint to recall, okay, I have the 5th root of 4 here, and I have the 5th root of x squared here. So what do you think you would get? Well, hopefully you're saying that we can just use the multiplication of radicals property to piece these back together to be 4x squared root 5, which you could get right from here, just taking the 5th root of it. But typically we want them in rational exponents just because you're going to see these are a lot easier to work with, especially when I'm multiplying radicals together and doing any kind of algebraic operation on them. It's sometimes easier to have it written out as rational exponents as opposed to radicals, but either of these are fine. Either of these, unless they tell you how they want the answer, either of these are fine with me. All right, the power of a quotient. Again, this one also behaves similar to distribution, but not exactly. What we do is we apply the 1/3 exponent to the numerator and the denominator. We could simplify the numerator to be x to the 2/3 power over 3 to the 1/3 power. Now, you might say to yourself, well, hold on now. This technically isn't in the most simplified form. So for example, let's rewrite this in terms of radicals. So maybe I'll change colors up here. And let's write this in terms of radicals. That's x squared to the 1/3 power over, oops, running out of space here, over the third root of 3. Okay. And you'll notice, wait a minute. I have a radical in the denominator. We cannot have this, cannot have a radical in the denominator. So, what should we do? Well, we're going to have to rationalize this. We're going to have to take the cube root of x squared over the cube root of 3, and we're going to have to multiply the top and bottom. Take a minute, test yourself. What do you think we have to multiply the top and bottom by to get rid of the radical in the denominator? Okay, hopefully you had some time to think about this and you realize, okay, I have the cube root of 3. I have to multiply the cube root of 3 by something to turn it into a perfect cube. So, let's see, if I multiplied that by the cube root of 3 squared, and if I multiply the top by the cube root of 3 squared, we would end up with, let's see, that's 9x squared, and I'm taking the cube root of that, all over, well, I have the cube root of 3 times 3 squared, so that's the cube root of 3 cubed, which is ultimately going to simplify down to 3. So this is the simplified version of what we want. If you wanted to work with rational exponents, you could do the same thing. If this would work, you would just have to multiply this side by 3 to the 2/3 power. And you would see when you add these together, oh, wait a minute, I end up with, so let's see, I have 3 to the 2/3 times x to the 2/3 all over 3 to the, well, if I take a third and I add 2/3, I get 3 to the third, which is 1. Hopefully it's starting to make sense to you. Really, we just have to make sure that our final answer doesn't have a rational exponent in the denominator. Just make sure there is no rational exponent in the denominator, because as we saw over here, a rational exponent in the denominator means you have a radical in the denominator, and that's not fully simplified. We are going to have to break it down further. Now, sometimes students find it easier to convert it to radicals, like in the green. They sometimes find, that's pretty easy for me. I'm able to think of it that way. Other students are like, no, I prefer to think of it like this blue work, where I convert it into rational exponents, and then I just work by adding some exponents to it. Your call, but the final answer should be in the most simplified form. Okay, now let's chat about negative exponents. And what do we do when we have a negative exponent? So I have x to the negative 2/3. Should that be x to the 1 over 2 times 3 power? Because I have a negative 2 on the top of a fraction. Doesn't that mean I move it down? No, it does not. Please make sure you do not do this. Instead, what we're going to do, we say, okay, a negative exponent, if I think back to x to the negative 2 power, this just meant I take 1 over x squared. Anytime something was affected by a negative exponent, we just put it to the other side of the fraction line. So, same thing here. I'm going to take 1 over x to the 2/3 power. And that's all that I'm going to do for right now. What we're saying here with negative exponents is the same thing as we said before. Just go ahead and, oops, looks like I have to, wow, guess I have to select a very specific color. No, just pick that one. Okay, there we go. All that we're going to say here, with negative exponents is that we're going to do the same thing as before. Push the exponent, or push the term that has a negative exponent to the other side of the fraction line. Just put it in the denominator, or maybe move it from denominator to the numerator. Put it to the other side of the fraction line and turn the exponent positive. However, you'll notice, wait a minute, problem, there's a rational exponent in the denominator. That means there's a root in the denominator. There's a radical. I can't have that. So, all we have to do is multiply the top and bottom by something to get rid of that. What do I want to multiply x to the 2/3 by to get rid of this pesky fraction? I want to turn it into a whole number. I don't want there to be a root, because if there's a fraction, if there's a denominator, that means I'm taking a root. I don't want that. So what should we multiply it by? Hopefully you're thinking, well, if I multiply it by x to some power, that means I'm going to be adding these exponents together. So what do I have to add to 2/3 to get it to be a whole number? Well, the easiest option is 1/3. So if I did this to the top and the bottom, let's see. On the numerator, obviously, I would just get x to the 1/3 power. But in the denominator, I would get x to the, let's see, 2/3 plus 1/3 is 3/3. But wait a minute, the 3/3 power, that's just 1. So there we go. I have x to the 1/3 power over x to the first. Again, if you wanted to write this as a radical, you could say that's the third root of x over x. But really, in rational exponents, this is the most simplified form. I will be checking to make sure that we don't write stuff that has a radical in the denominator. We do not want to just leave our answer like this, okay? So make sure you simplify it as much as you can. Last property we're going to talk about is the zero exponent property. What happens if I have x to the 0 over 2 power? Well, x to the 0 over 2 power is just 0, right? And then that's just going to be 1. Because anything to the 0 power is 1. So even if I put it in a fraction, really, it's because 0 divided by 2 can be simplified to 0. That's why all I'm doing is turning it into 1. Remember, anything to the 0 power is 1. Okay, side note, except for 0 to the 0 power. Anything to the 0 power is 1, except if I took 0 to the 0 power. That's a different story. We've explored a little bit in class about that, but that's a different story. And that this could equal a number of things, but for our sake, we're just going to say it's undefined. Now, let's go ahead and try practicing some of these problems. Take a few minutes, look over a few of these different problems, and go ahead and practice them to yourself and see what you get. Okay, well, hopefully you had some time to practice on these, but let's go ahead and start simplifying them. In the first one, I'm seeing that I am taking 2, and I'm going to multiply that by 3, and then I have x and multiply that to 3/4, and x to the 5th. I'm just rearranging the terms here. I'm using the associative property of multiplication. This is just, you can rearrange the terms. So I'm going to multiply the 2 and 3 together to get the 6. And I'm going to multiply the 3/4 and the 5/4 together to get x to the 8/4. All that I'm doing is my multiplication of like bases. Since I'm multiplying the same bases together, I'm going to add their exponents together. I'm going to add their exponents together. So, when I add their exponents together, I get 8/4. Now, you would probably notice that 8/4 just simplifies to 2. And it does. This is an easy way of going and simplifying radicals. Before, you might have had x to the 8th power to the 4th root. And you might have gone through and made 1, 2, 3, 4, 5, 6, 7, 8 x's, and then you had made a group of 4 and another group of 4, and broken that down to eventually get x squared. But this right here is a very quick, easy, and simple way of seeing why x to the 8th to the 4th root is just x squared. You're just dividing. Okay, let's go ahead and start with this one now. 12 divided by 3 is 4, and then I'm going to take y to the 5/8 divided by y to the 4/8. Well, the division of like bases says if you're dividing like bases, all you need to do is to subtract their exponents. So we should get 4y to the 1/8 power. And that should just be the final answer. All we did was subtract the exponents from the y's and divide the 12 and 3. Now let's take a look at 4x to the 4th to the 1/2 power. This is really saying what's the square root of 4x to the 4th. But if I'm using the rational exponents, what we can do is we can apply that exponent to each of the terms in the parentheses. And remember, I'm taking a square root here, so what's 4 to the 1/2 power, or the square root of 4? 2. And what's x to the 4th to the 1/2 power? Well, let's just multiply those together to get x to the 4/2. Oh, wait a minute, that's just x squared. Notice that I multiplied the exponents here. I used the power rule to multiply the 4½ to get 4 over 2, and then simplified that to x squared. And that should make sense, because if I'm taking the square root of all this, what's the square root of 4? 2. What's the square root of x to the 4th? X squared. It should work out the exact same way. Okay, now let's make it a little more complicated. Let's have a negative exponent thrown in here. The first thing we have to do, we should always do really, is take care of the negative exponents first. So I'm going to put here the 5x squared y on the bottom to the 1/2 power. This way I'm saying, wait a minute, I have this in the bottom, it's good to go. But then I could go and start, I don't know, what should we do first? We could go and start applying the 1/2 to everything, but you'll notice, wait, we got a radical in the denominator. So does it best suit us to, I guess you could say, rationalize the denominator right now? Or should we just go ahead and start simplifying? Well, we'll figure it out. Let's just go ahead and start applying the 1/2 to everything. So that's 5 to the 1/2 power, that's x to the 1st, and that's y to the 1/2 power, under 1. Okay, I'm going to do something here where I'm going to group a couple of these things together, because I think it might be easier if we saw the stuff to the 1/2 power all together. Okay, now I have to multiply the top and bottom by something to get rid of these rational exponents. So I'm going to multiply them by 5 to the 1/2 and y to the 1/2. This stylus is terrible. Oh my gosh, whatever. So all we're doing is we're multiplying both sides by 5 to the 1/2 and y to the 1/2. Because I want to get 5 to have a whole number exponent, and I want y to have a whole number exponent. So when we're done, we should have on the bottom x. 5 to the 1/2 times 5 to the 1/2 is, well, 5 to the 1st. Y to the 1/2 times y to the 1/2 is y to the 1st. And then on the top, we just have 5 to the 1/2 power and y to the 1/2 power. So if I was to make this probably a little neater, I could say that's 5 to the 1/2, y to the 1/2 over 5xy. And here we go. We've gone and rationalized the denominator. We're making sure that there is no root in that denominator. And by making sure there's no root in the denominator, we're also making sure that there's no fraction exponent. There's no denominator exponent in the denominator. Okay, so If you have any questions on what you're seeing here or comments about the video, feel free to send me an email. My email is klinford@wccnet.edu. Feel free to let me know what you think. If you have any questions, feel free to get in contact with me. Until next time, take care.